Right now, as you watch this, seismometers buried beneath Yellowstone National Park are recording something. Not an earthquake. Not yet. Just the breathing of the caldera. Small tremors, imperceptible to the 4 million people who visit each year, but constant, measurable, alive. Beneath those geysers and boardwalks sits a magma chamber the size of Rhode Island, less than 5 miles below the surface. Not a volcano. A supervolcano. The ash fallout zone from a full eruption would blanket tens of millions of people across half the continent. For years, scientists monitored it and asked the same question: why hasn't it erupted? Now they finally have an answer. They've identified the mechanism holding the lid on, barely. And they've confirmed something else. It won't last. To understand what they found and why it changes everything, we need to go back to the moment geologists realized Yellowstone was a volcano at all. In late 2023, a team from the University of Utah and the United States Geological Survey published new seismic imaging of Yellowstone's magma reservoir, the most detailed picture yet. Using thousands of sensors and years of data, they mapped the melt fraction, liquid magma versus solid crystal. They confirmed something critical. The chamber is mostly solid, a crystalline mush, not a lake of liquid rock. That sounds reassuring. It is, on the surface. But the study also confirmed the thin layer of melt that does exist is enough. And the crustal lid holding pressure in check is thinner in areas than models predicted. This isn't speculation. This is peer-reviewed science from the institutions monitoring Yellowstone around the clock. But here's the promise I'm making you before we go any further. Over the next minutes, we'll separate fact from fear. We'll examine why Yellowstone is quiet today, what scientists have found beneath it, and what would have to change before an eruption became possible. No sensationalism, no guessed dates, and no made-up disaster numbers. Just the data, the scientific debate, and the real stakes for millions living in the shadow of North America's largest volcanic system. Some answers are reassuring, others are not. But each comes from researchers who study this place every day. But first, I want to hear from you. Have you ever visited Yellowstone? Or do you live in Wyoming, Montana, or Idaho? Tell me in the comments where you were and whether you felt any tremors. The park records hundreds of small earthquakes monthly. If you live in or near the volcanic risk zone, or know someone who does, subscribe and hit, so this reaches people who need it. You're part of a community that chooses to know. Because for most of history, no one even knew there was a volcano here. In 1965, a young geologist named Bob Christensen arrived at Yellowstone with a simple assignment: map the volcanic rocks. What he found instead was a mystery that would rewrite everything scientists thought they knew about the American West. The clues were subtle at first. Yellowstone had geysers, hot springs, and steam vents, clearly volcanic. But where was the volcano? Every volcanic region Christensen had studied had a mountain. A cone, a clear central point where lava had erupted. Yellowstone had none. Instead, he found something unsettling. The park's geothermal features formed a rough oval stretching 30 miles north to south and 50 miles east to west. Not scattered randomly, but arranged in a pattern, as if following the rim of something enormous. Christensen began mapping the rhyolite flows, the signature rock of explosive eruptions. The flows were ancient, but massive, far larger than anything he'd seen, and they all seemed to originate from the same general area, the center of that oval pattern. The breakthrough came from the air. Flying over Yellowstone in small planes, Christensen and his USGS team could see what was invisible from the ground. The entire central region of the park sat lower than the surrounding mountains. Not a valley carved by rivers, but a depression so vast that standing inside it, you couldn't see the edges. They were looking at a caldera, but not just any caldera. Picture this. You're standing at the rim of Crater Lake in Oregon, one of the most famous calderas in the world. 6 miles across, formed when Mount Mazama collapsed 7,700 years ago. Now imagine a caldera 8 times larger. So large that if you stood on one rim, the opposite edge would be beyond the horizon. That's what Christensen realized he was looking at. The entire central region of Yellowstone, the geyser basins, the roads, the visitor centers, the hotels, everything sits inside the collapsed mouth of a volcanic system orders of magnitude larger than anything in recorded human history. But there was more. Drilling core samples and analyzing the rock layers, the team found evidence of not one, but 3 catastrophic eruptions. The most recent had happened 640,000 years ago. Before that, 1.3 million years ago. Before that, 2.1 million years ago. The pattern was chilling. Roughly every 600,000 to 800,000 years, this system had exploded with enough force to bury much of the continent in ash. Let that sink in for a moment. Every tourist who stands at Old Faithful, every family that camps in the backcountry, every ranger who works there, they're all inside the mouth of a supervolcano. The geyser they're watching isn't separate from the volcanic threat. It's a symptom of it. When that last eruption happened 640,000 years ago, the collapse created a depression 30 by 45 miles across. The ash cloud reached both coasts. The blast was 2,500 times larger than Mount St. Helens. If it happened today, the initial ashfall would bury everything within 100 miles under several feet of volcanic debris. Christiansen's team had discovered something unprecedented in North America. A supervolcano, not dormant, but sleeping. The hydrothermal features that draw millions of visitors each year, the geysers, the hot pools, the steam, are powered by the same magma chamber that feeds the eruptions. The real danger had been hidden in plain sight. Tourists photograph Yellowstone's beauty, unaware they're documenting the breathing of one of the most powerful geological forces on the planet. This wasn't an ancient, extinct system. The seismic monitoring that began after Christensen's discovery showed the caldera rising and falling like a sleeping giant's chest. Some years it bulged upward several inches, other years it deflated, always moving, always changing. Earthquakes rattled the region constantly, most too small to feel, but recordable by sensitive instruments. The magma chamber below was active, dynamic, connected to the deep plume of heat rising from the Earth's core. But here was the puzzle that haunted Christensen and every volcanologist who came after him. If this system was still active, if it had erupted roughly every 600,000 to 800,000 years, and if the last eruption was 640,000 years ago, why hadn't it erupted again? The math was simple. The pattern suggested another eruption was not just possible, but overdue. Yet Yellowstone remained quiet, its geysers performing on schedule, its wildlife thriving, its tourists blissfully unaware of what churned beneath their feet. So why hasn't it erupted again? The answer lies in what's happening 5 miles below your feet. To understand what's preventing an eruption, you need to picture what's happening 400 miles beneath Yellowstone. Deep in the Earth's mantle, a column of superheated rock rises like a massive blowtorch, a mantle plume or hotspot that has burned in the same spot for millions of years. But the North American continent doesn't stay put. It drifts southwest at roughly 2 inches per year, like a sheet of paper sliding over a candle flame. The hotspot stays fixed. The continent moves. Think of it as a geological conveyor belt. 16 million years ago, this same hotspot was beneath what's now eastern Oregon and western Idaho, creating the Columbia River flood basalts. As the continent drifted, the hotspot burned through, leaving a trail of calderas across southern Idaho, like a torch cutting through metal. Today, that torch sits directly beneath Yellowstone. The heat from this plume melts the crust above it, creating a magma chamber of staggering size. We're talking about 55,000 cubic kilometers of molten and semi-molten rock. To put that in perspective, Mount St. Helens, which devastated hundreds of square miles in 1980, involved less than 1 cubic kilometer of magma. Yellowstone's chamber is 55,000 times larger. If that erupted all at once, it would release energy equivalent to thousands of thermonuclear weapons detonating simultaneously. But here's what recent seismic imaging has revealed, and it changes everything. That chamber isn't filled with liquid magma waiting to explode. It's mostly solid. Think of it as a giant sponge made of crystals, with only 5 to 15% liquid melt scattered throughout. Not an underground lake of lava, but a crystalline mush, hot enough to stay partially molten, but not mobile enough to erupt catastrophically. This discovery came from analyzing thousands of earthquake waves that traveled through the chamber. Just like X-rays passing through a body, seismic waves move differently through liquid than through solid rock. The data was clear. Most of Yellowstone's magma chamber has crystallized into a matrix too thick to flow rapidly. But there's a second mechanism keeping Yellowstone stable, and it's just as important. Above the crystallized chamber sits a thick cap of rhyolitic rock, essentially volcanic glass that cooled and hardened from previous eruptions. This lid is incredibly viscous, thousands of times thicker than honey, and it seals the chamber like a pressure cooker cap welded shut. For an eruption to occur, 2 things would need to happen. First, enough liquid magma would need to accumulate, either from new magma injection from below or from remelting of the existing crystals. Second, that magma would need enough gas pressure to fracture through the thick rhyolitic lid above. Right now, neither condition exists. The chamber remains mostly crystallized, and the lid remains intact. This is why Yellowstone's hydrothermal features, the geysers, hot springs, and fumaroles, are actually good news. They're pressure relief valves, allowing heat and gas to escape gradually through the groundwater system. As long as that system keeps working, catastrophic pressure buildup becomes much less likely. The scientists who monitor Yellowstone 24 hours a day know exactly what to watch for. Rapidly escalating earthquake swarms, dramatic ground deformation as magma pushes upward, and changes in the gas chemistry of the hydrothermal features. None of those warning signs are present today. In fact, Yellowstone is doing exactly what a stable, crystallized magma chamber should do. The ground rises and falls in predictable cycles as the chamber breathes with seasonal pressure changes. Earthquakes occur regularly, but they're small, the kind you'd expect from thermal expansion and contraction, not from rising magma. The discovery of the crystallization state was a genuine revelation. For years, scientists had modeled Yellowstone as a bomb waiting to go off. The reality is far more nuanced. It's a mostly solid mass that would require extraordinary circumstances to become mobile again. That sounds reassuring, and for now it is. But here's what the same research revealed. When Yellowstone last erupted 640,000 years ago, the North American continent was essentially empty. A few thousand indigenous people scattered across millions of square miles. The ash cloud that buried the Great Plains fell on grasslands and buffalo herds, not cities and farmland. Today, that same eruption would occur in a fundamentally different world. The USGS Volcano Hazards Program has modeled the ashfall pattern using wind data and eruption mechanics from the last super eruption. Within 500 miles of Yellowstone, ash accumulation would range from several inches to several feet, enough to collapse roofs, clog water treatment facilities, and bring all ground transportation to a complete halt. That 500-mile radius includes Salt Lake City, Denver, Billings, and Rapid City. Cities where millions of people live, work, and depend on just-in-time supply chains that would fail within hours. But the devastation extends far beyond that inner circle. Within 1,000 miles, cities like Kansas City, Oklahoma City, and Minneapolis would face inches of ash, enough to contaminate water supplies, ground aircraft indefinitely, and shut down the electrical grid as ash shorts out transformers and clogs cooling systems. If you live in Denver, your air, water, and food supply would be cut off within days. The city's reservoirs would be contaminated with ash that acts like concrete when wet. Interstate 25 and Interstate 70, the major supply arteries for the entire region, would be impassable for months. The economic projections are staggering. FEMA's regional assessments estimate initial casualties in the tens of thousands within the immediate blast zone, but the infrastructure collapse would affect tens of millions. The immediate economic damage alone would reach into the trillions of dollars, more than Hurricane Katrina, the 2008 financial crisis, and COVID-19 combined. But that's just the beginning. The ashfall zone encompasses the heart of America's agricultural breadbasket. Wheat fields across Montana, North Dakota, and eastern Colorado would be buried under toxic ash. The disruption to food production could last multiple growing seasons, as ash makes soil too alkaline for crops and contains fluorine compounds lethal to livestock. Then there are the climate effects. The last Yellowstone eruption ejected so much sulfur dioxide into the stratosphere that it triggered a volcanic winter, where global temperatures dropped for several years. In our interconnected modern world, even a temporary cooling of global agriculture would trigger famine across regions that import American grain. The most sobering detail? Most American communities in the ashfall zone have no volcano-specific emergency plans. Ask your local emergency management office if they've planned for volcanic ash, and you'll likely get a blank stare. Compare that to Japan, where volcanic eruptions are a fact of life. Japanese cities conduct regular drills. Buildings are constructed with ash loads in mind. Citizens keep ash masks in their emergency kits. Public transportation systems have protocols for ash cleanup. The country maintains strategic food reserves specifically for volcanic emergencies. Here in the United States, we've planned extensively for hurricanes, tornadoes, and earthquakes. But volcanic ash? Most emergency managers have never considered it. The assumption has always been that major volcanic threats, like Yellowstone, are too rare to plan for. That assumption may be costly, because while the crystallized magma chamber offers reassurance about immediate eruption risk, it doesn't eliminate the risk entirely. The mechanisms keeping Yellowstone stable today are geological processes, not physical laws. They can change. And the research that discovered these stabilizing mechanisms also revealed something else, evidence that the situation is not as permanent as scientists initially hoped. Which brings us to the question no one wants to ask. When? Remember that crystallized magma chamber we just described, the mostly solid mass that's keeping Yellowstone stable? Here's what the same research teams discovered about it. Crystallization is reversible. Think of it as a dam holding back a reservoir, except the dam itself is made of ice. Right now it's solid and strong, but it's also melting. Recent modeling from Stanford University and the USGS shows that the crystallized chamber can remobilize far more rapidly than anyone previously understood. Not over millions of years, over decades to centuries. If fresh magma intrudes from the mantle plume below, it acts like a heat source in an ice storm, converting crystals back to liquid. The process is surprisingly efficient. Computer models show that a magma injection representing just 5% of the chamber's total volume could remobilize enough liquid to create eruptible conditions. 5%. That's the difference between stability and catastrophe. But there's a second problem. The protective lid itself is weakening. The rhyolitic cap that seals the chamber isn't static. It's being slowly dissolved by the same hydrothermal activity that creates Yellowstone's famous geysers. Every hot spring, every fumarole, every steam vent represents groundwater circulating through that protective layer, gradually thinning it through chemical weathering. Recent ground-penetrating radar and seismic studies have identified areas where the lid has thinned substantially. Like rust eating through steel, the process is slow but relentless. Even more unsettling, analysis of volcanic deposits from previous Yellowstone eruptions shows that some occurred when the magma chamber was in a similar crystallized state to today. The mostly solid condition that seems so reassuring? It's not a permanent shield. Past eruptions prove that even crystallized chambers can find ways to explode catastrophically when conditions align. The scientists monitoring Yellowstone today understand something the public hasn't fully grasped. Stable and safe are not the same thing. The current stability is a dynamic equilibrium, not a static lock. Every small earthquake, every hydrothermal pulse, every fluctuation in ground temperature represents the system's ongoing evolution. The mechanism preventing an eruption today could fail during your lifetime, or your children's lifetime, or it could hold for 10,000 more years. The mathematical models can predict how the system could destabilize, but they cannot predict when. What makes this particularly haunting is the timescale uncertainty. Geological processes operate on schedules that make human planning nearly impossible. We prepare for hurricanes that come annually, earthquakes that strike every few decades. But how do you prepare for a threat that could manifest tomorrow or in millennia? The clock is ticking. We just don't know how much time is on it. And that uncertainty is exactly where the myths begin. Let's address the biggest myth about Yellowstone directly, the idea that it's overdue for an eruption. You've probably seen headlines claiming Yellowstone erupts every 600,000 years, and since the last eruption was 640,000 years ago, we're 40,000 years past schedule. That's not how volcanoes work at all. The USGS has stated this explicitly. Yellowstone is not overdue. 3 eruptions, 2.1 million, 1.3 million, and 640,000 years ago, do not establish a reliable schedule. That's not statistical data, it's barely a pattern. The intervals were 800,000 years, then 60,000 years. If anything, the trend suggests longer gaps, not shorter ones. Volcanoes don't operate on timers. They respond to physical conditions, magma supply, crustal stress, gas pressure. Those conditions could align tomorrow or in 100,000 years, regardless of when the last eruption occurred. But there is a genuine scientific debate about Yellowstone's future, and it's worth understanding both sides. Some researchers, including teams from the University of Utah, argue the system may be winding down. They point to evidence that the mantle plume beneath Yellowstone is cooling and losing intensity. The total melt fraction in the magma chamber has decreased over geological time. Some models suggest Yellowstone may be transitioning toward dormancy, like the older calderas the Hotspot created as it tracked across Idaho. Other researchers disagree. They point to ongoing seismicity, measurable ground deformation, and robust hydrothermal activity as evidence that the system remains very much alive. Recent studies have documented new magma intrusions, and the overall heat output from the caldera shows no signs of decreasing. The truth? Both groups are looking at the same data and reaching different conclusions. That's not scientific incompetence. It's the nature of studying a system this complex with only modern instruments and limited historical data. Now, could Yellowstone erupt tomorrow without warning? Probably not. The monitoring network surrounding Yellowstone is among the most sophisticated on Earth. Dozens of seismometers, GPS stations, gas sensors, and thermal cameras operating continuously. Precursors to a super eruption, escalating earthquake swarms, rapid ground uplift, dramatic changes in gas chemistry, would almost certainly be detected. But the warning time could be weeks, months, or in a worst-case scenario, days, not years, not the comfortable buffer that emergency planning typically assumes. Here's what the USGS actually says about probability. The annual chance of a Yellowstone super eruption is roughly 1 in 730,000. You're statistically more likely to be struck by lightning, die in a car accident, or experience a major earthquake in California. You're also more likely to see a smaller eruption at Yellowstone, a lava flow or localized explosive event that would be devastating locally but not globally catastrophic. Those events are far more probable than a super eruption. I'm not here to tell you Yellowstone will erupt next year. I'm here to tell you what scientists actually know and what they don't. The uncertainty is real, the monitoring is excellent, and the immediate risk is low. Because the real lesson isn't about predicting the eruption, it's about what we choose to do before it happens. Nature sets the hazard, but humans set the death toll. Consider what happened 74,000 years ago when the Toba supervolcano erupted in what's now Indonesia. The genetic evidence suggests the human population dropped to as few as 3,000 to 10,000 individuals worldwide. We nearly went extinct, not from the blast itself, but from the volcanic winter that followed. Early humans had no warning, no understanding of what was happening, and no way to preserve food or maintain warmth during years of dim sunlight. A Yellowstone supereruption today would occur in a fundamentally different world. We have satellite monitoring that can track ash clouds in real time and predict their movement days in advance. We have global supply chains that can redirect food production from affected regions to unaffected ones. We have strategic grain reserves, genetic seed vaults in Norway and elsewhere, and pre-positioned disaster response capabilities that dwarf anything available even 50 years ago. But preparation isn't automatic. It's a choice. Look at the contrast between American volcanic preparedness and countries like Iceland or Japan. In Reykjavik, building codes account for ashfall loads. Citizens keep volcanic ash masks in their emergency kits alongside flashlights and batteries. When Eyjafjallajökull erupted in 2010, Icelandic communities implemented well-rehearsed protocols for dealing with ash cleanup, air filtration, and livestock protection. In Japan, volcanic drills are as routine as earthquake drills. Cities near active volcanoes maintain ash removal equipment and emergency food supplies specifically for volcanic events. Public buildings are designed with volcanic scenarios in mind. In contrast, most American communities in the Yellowstone Ashfall Zone have never conducted a volcanic emergency drill. Our buildings aren't designed for ash loads. Our emergency supply chains assume normal transportation networks will remain functional. The outcome of a Yellowstone eruption isn't predetermined. It's a function of choices we make now while the system remains quiet. The technology exists to minimize casualties. The agricultural techniques exist to maintain food production in affected areas. The engineering solutions exist to build ash-resistant infrastructure. The question isn't whether we can survive a super eruption. The question is whether we'll choose to prepare for it. So what does preparation actually look like for you, personally? Preparation for a Yellowstone eruption isn't about bunkers or doomsday scenarios. It's about practical, sensible steps that work for any extended emergency situation. If you live in the potential ashfall zone, which includes most of the western and central United States, focus on sheltering in place for at least 2 weeks. Stock water, 1 gallon per person per day, non-perishable food, and most importantly, respiratory protection. N95 or 100 masks are absolutely essential because volcanic ash isn't like snow. It's pulverized rock and glass, abrasive, toxic to lungs, and conductive when wet, meaning it shorts out electrical systems throughout entire regions. Plastic sheeting and duct tape should be in your emergency kit to seal windows and doors effectively. Ash infiltrates everything. A battery-powered or hand-crank radio becomes critical when electrical grids fail from ash accumulation on power lines across wide areas. If you live in Wyoming, or parts of Montana and Idaho within the immediate geological hazard zone, your priorities shift significantly. Have an evacuation route planned and practiced. Understand that major roads may become impassable quickly. Maintain an out-of-state emergency contact who can coordinate family communications. Sign up for the USGS Volcano Notification Service. Real alerts from real scientists, not social media speculation or fear-mongering. Consider your insurance coverage carefully. Standard homeowners policies typically exclude volcanic damage. Ask your agent about volcanic coverage options, especially if you live within 500 miles. At the community level, ask your local emergency management office a simple question. Does our city have a volcanic annex to its emergency plan? Most don't. That's a conversation worth starting. Remember this fundamental truth. Most deaths in volcanic disasters come from unpreparedness and panic, not from the actual eruption itself. People die from collapsed roofs that weren't built for ash loads, from respiratory failure because they didn't have proper masks, from dehydration because they didn't store adequate water supplies. You can't control the massive magma chamber 5 miles beneath Yellowstone. You can't control when crystallization might reverse or when the protective crustal lid might weaken. But you can control whether you have a mask and a plan. Because in the end, this isn't really a story about a volcano. Yellowstone will erupt again. That's geology. But how many people die? How many communities recover? How much we lose? That's not written in the rock. That's written in the choices we make right now while the ground is still quiet. The discovery of what's keeping Yellowstone stable today isn't a reason to relax. It's a reminder that we live on borrowed time, and that time is a gift we can use to prepare. The crystallized magma chamber, the protective lid, the monitoring networks, all of these give us something previous generations never had: advance warning and time to act. It's okay to feel uneasy after watching this. That unease is useful if it moves you to act. Fear becomes wisdom when it drives preparation instead of paralysis. Tell me in the comments where you live and whether this changes how you think about preparedness. Are you in the ashfall zone? Do you have supplies? Does your community have a plan? If this video reached you, help it reach someone else. Subscribe and like, so the algorithm shows this to people who live near volcanic threats. Not just Yellowstone, but the Cascades, Alaska, Hawaii. Knowledge shared is knowledge multiplied. Beneath the geysers and the bison and the tourists taking selfies, the Earth is still dreaming. The magma chamber rises and falls like a sleeping giant's chest, breathing in geological time. And when it finally wakes up, the only question that will matter is, were we ready?